Welcome to Paradigms of Computer Programming. I'm Peter Van Roy, and I will be teaching this two-course sequence. So there are in fact two courses, Louvain 1.1x, which is the course you're following now, and Louvain 1.2x, which is the follow-on course that starts just after. So together, these two courses teach programming as a unified discipline that covers all or very large number of programming languages. This is a very ambitious goal. You might be wondering how we can achieve this in this particular sequence. Well, in this video, I'm going to explain exactly how our approach works. The courses have a second-year university level. They require some programming experience, but not so much. You have to have written some small programs in at least one programming languages. Also, a little bit of mathematics, discrete mathematics, sets, lists, functions. That's about all you'll need. The courses will cover four themes. So in Louvain 1.1x, we cover functional programming and formal semantics, which is in some sense the apotheosis of this course. So in functional programming, we will also cover important basic data structures and techniques, and formal semantics will talk also about computational complexity. This is essentially how the execution time or space of your program changes when the input size increases without bounds. And in Louvain 1.2x, we will continue and we'll talk about data abstraction and concurrency. So object-oriented programming is covered as part of data abstraction, and in the part on concurrency, we'll talk about a particular very nice way of doing concurrent programming called deterministic data flow. Let's now see how we're going to do this in practice. So in practice, there are hundreds of programming languages in realistic use all over the world in industry in many applications. In this slide, I've shown some of them. In fact, I've picked the ones with very nice icons. So you can see already there's a whole bunch of them here. You recognize probably many of them. So how can we cover all of these languages? How can we understand them all? So we have this huge number of languages. How can we understand them all? So the key insight of this course is that languages are based on what we call paradigms. And there are many fewer paradigms than languages. So in order to understand hundreds of languages, we don't have to understand so many paradigms, a much smaller number. And in fact, each paradigm consists of a set of concepts. So even two paradigms that might seem very different might have concepts in common. So we have a small set of paradigms and an even smaller set of concepts. So that's the key insight. But before going on, let me explain what is a programming paradigm. So a programming paradigm is an approach to programming a computer based on a coherent set of principles, or if we have already some deeper understanding, a mathematical theory. So for example, functional programming, the theory is called lambda calculus. Multi-agent concurrent programming, the theory is called pi calculus. Object-oriented programming has several different kinds of theory, but it's essentially organizational theories of how to structure information and update information. So these are some different programming paradigms. So when we actually write a program, though, we're not interested in paradigms as such. We're interested in solving problems. Let me give an example. Let's say we want to build a house. Well, we have to think about the masonry. How do we build it? We have to think about carpentry, the woodwork. We have to think about plumbing. We have to think about electricity. We have to think about heating. And so there are a number of different disciplines or ways of thinking that you have to combine when building a house. Well, it's the same for writing a program. So a large program, anything bigger than toy programs, so it has to solve many problems, okay? And each kind of problem needs its own kind of a paradigm. So the point is, we need multiple paradigms in the same program, and we need to combine them. They don't live separately. So how can we do this? The first question, how can we study in this course, in this one sequence of two courses, how can we study multiple paradigms? How can we study multiple paradigms in the easiest possible way? One way would be to study multiple languages. But this actually, it might seem like a good approach, but actually it's not practical. And the reason is the following. Each language has its own syntax, its own semantics, behavior, its own system that we have to install, and its own funny quirks that we have to get used to. And we could pick 3 languages, for example, Java, Erlang, and Haskell, representative of 3 useful paradigms, and structure our course around them. But this would make things complicated for no really good fundamental reason. We would have to install 3 systems, get used to 3 syntaxes, and even then the languages would not be able to talk to each other. So it would be very hard to combine them. So we are not going to use this approach. We are going to use another approach based on research that has been done in the last 20 years. We're going to use one language, a research language called Oz, designed to support many paradigms. So this is 20 years of work by an international community of researchers in programming language design and implementation. And we have written a textbook, Concepts, Techniques, and Models of Computer Programming, that uses Oz to cover very many paradigms. So the point of the course is not really to learn Oz. We hope that Oz will, in some sense, get out of the way so we can focus on the paradigms and how they can be combined. Okay? So we get then to the second question, which is how? How can we combine different paradigms in one program? Any realistic program needs to solve different problems, so needs different paradigms and different parts. Each paradigm is a different way of thinking. How can we combine different ways of thinking in one program? Well, the approach that we will use is called the kernel language approach. And it's because in our research we find that each paradigm has a simple core language called its kernel language that contains the essential concepts. So even complicated, realistic, practical languages with lots of bells and whistles can be translated into a kernel language which is simple. And then we notice that even very different paradigms have kernel languages that have much in common. And often only one concept makes all the difference. So for example, between functional programming and deterministic data flow concurrency, there is one concept. Between functional programming and object-oriented programming, there's also one concept, a different one. So there is a lot of commonality even between paradigms that seem very different. So what we'll do is we will start with a simple paradigm, the simplest one. So our first paradigm will be functional programming, which has the simplest kernel language. And then we will add concepts one by one to give the other paradigms. So this is in some sense an application of the scientific method, understanding a system by decomposing it into its component parts and then bringing those parts together. So let me briefly then summarize the approach. So first of all, hundreds of languages. We can't learn hundreds of languages. Solution, focus on paradigms, since there are many fewer paradigms than languages. Then going on, one language per paradigm is already too much, since the languages are complicated and they can't talk to each other. Solution, using one research language that can express many paradigms that is simple. Also, going on, realistic programs need to combine paradigms. How can we do it? Well, solution, we define paradigms using kernel languages. And since the kernel languages have much in common, this lets the paradigms talk to each other. There is a common language between even two different paradigms. So this is very economical. So now, this is kind of the philosophical discussion on paradigms. Let's now become more concrete. Let's get started. Probably you already know an object-oriented language, since object-oriented programming is extremely popular. It's probably the most popular paradigm. So object-oriented programming has a set of coherent principles that have been developed over years, and it's clearly an important paradigm. But what about the other ones? Isn't object-oriented programming by far the most important useful paradigms? Why are we even looking at other paradigms? Actually, object-oriented programming is not the most important and useful paradigm. It's not at all. Many other paradigms are extremely useful and often much more useful than object-oriented programming. For example, if you want to make a robust and efficient distributed programming running over the internet, object-oriented programming just does not give you the right tools to solve the problem. You have many kinds of things you need to do. Synchronization, you have to coordinate things, communication, there's asynchronicity, there's latency, and so on, so on. There's failures, fault tolerance. Object-oriented programming is just not the right set of tools. It's like trying to use a screwdriver to solder an electrical circuit. It doesn't work. It just doesn't work. So another paradigm called multi-agent data flow is actually much more suited to building internet programs. So in this course, in fact in these two courses, we will cover 5 paradigms, and together these are in some sense, in our view, the most important. They solve very many interesting and important problems. So the 5 paradigms are the following. So functional programming, the base one, in fact in some sense it underlies the others. Object-oriented programming, the one everybody thinks they know. Deterministic data flow, the most interesting form of doing concurrent programming, also very simple. And now in the age of multi-core systems, more and more languages are introducing ideas from this paradigm because it's both powerful and extremely simple. Then multi-agent data flow programming. This is in some sense, in our view, the best overall general purpose paradigm for concurrent programming. So we couldn't leave it out, even though maybe it's a little bit too advanced to explain it all in this course. We just couldn't leave it out. So in fact, it's added as a bonus lesson in Louvain 1.2x. And then a 5th one, active objects, which essentially combines multi-agent data flow with object-oriented programming to take the advantages of both. So these are probably the most important general programming paradigms. But there are many, many others, okay, for other problems. So at the end of the second course, we'll explain a little bit how you can go on. And in the book, the textbook, there are many other paradigms as well that are explained. So we're going to cover 5 paradigms. In fact, we're going to cover many more ideas and concepts. So here we have a partial list. So on the left, we have the list for Louvain 1.1x, on the right for Louvain 1.2x. So here it starts, very simple, identifiers, environments, functional programming, recursion, invariant programming, the best way to do loops in any paradigm, important data structures, list trees, records, symbolic programming with other things than numbers, and then the foundation for all of the techniques of abstraction, higher order programming, genericity, instantiation, also issues of efficiency, complexity, big O notation, asymptotics, Moore's law, NP, NP-complete problems, and then semantics, mathematical semantics based on abstract machines, kernel languages. So this is all covered in Louvain 1.1x. In Louvain 1.2x, we go farther. We go into data abstraction, building on state, abstract data types, objects, polymorphism, inheritance, multiple inheritance, object-oriented programming, combining them, exception handling to handle unusual, rare situations without making the code cumbersome, concurrency, an extremely important concept, non-determinism, the demon we have to slay if we really want to use concurrency well, scheduling, fairness, data flow synchronization, deterministic data flow, and finally, multi-agent programming with agents and streams. So we're actually covering a wide variety. And the reason why we can cover it in this 2-course sequence, which is actually not so big, is because it's very well factored. Every concept is only explained in one place, its natural place. We don't have to repeat ourselves when we go from one paradigm to the other. So the next steps, so in the next video, we're going to talk about the practical organization. So the 6 lessons, 1 lesson per week. Also, the programming exercise is very important, that you do real programming exercises, that you're active. It's not enough to listen to videos and answer multiple choice. You have to create your own programs. And now we're going to start then with our first paradigm, which is functional programming.